this is how two reactions are represented graphically. Now on y-axis we have energy profile, and on x-axis we have progress of reaction. All right, now this is enthalpy of a reactant, goes uphill and then again comes down, forms enthalpy of product. This is called as activation energy. Now energy profile, right? So this is the energy which it had. Now if we go back to our reaction that we started, was the reactant has 1815 kilojoules. Now this is what is a reactant, HR, and this is what is product, HP, 1919 kilojoules per mole, and 1815 kilojoule per mole is reactant. All right, so coming back to our graph, so this is enthalpy of reactant, this is enthalpy of product. For a reaction to get into product has to cross this uphill route. Now this is enthalpy of reactant. If I draw a line from here and then take this is known as activation energy. So from here to here is the activation energy. So for a reaction to occur, you require activation energy. Otherwise, in environment we have so many gases there, right? Nitrogen, oxygen, carbon dioxide. So maybe nitrogen and oxygen can react with each other to form varieties of oxides of nitrogen. Could be detrimental, could be laughing gas. We would be keeping on laughing if laughing gas is generated. Why does this? Or nitrogen, if nitrogen is there and a little bit of hydrogen is there, ammonia would form. Now why does it not happen? It's purely because of this activation energy. This activation energy is taken care by catalysts. We use catalysts to quicken the rate of reaction, and also for reaction to occur. We use catalysts for reactions to occur, and if reactions already occur, then to quicken the rate of reaction. How? By reducing this activation energy. So this is the activation energy, very important criteria for reactions to occur. All right, so okay, getting back, HR carries this uphill route, comes here, forms HP. Now here is HP, here is HR. So del H is what? HP minus HR. When HP minus HR is positive, obviously now HP comes here in format of energy and HR comes here in format of energy. So HP is greater than HR, so obviously del H, the difference in enthalpy, would be positive. And if it is positive, then we call it as endothermic reaction, heat absorbed. All right, so when we did here, so when we saw this part, HP minus HR, we did that, and what we got is positive. So this is endothermic. All right, whenever this reaction occurs, the entire system becomes cool because it takes this much of heat from the system. All right, let's understand what is exothermic reaction now. It's the same thing, HR, HP, enthalpy of reactant, enthalpy of product. Now in this case, you find that HP comes down, enthalpy of product is much below. All right, much lower than that. So when we take the difference, it comes as negative del H. Why? HP is over here, HR is over here. So HP is lesser than HR. So as a result of that, we get HP minus HR as minus del H. Now this reaction is called as exothermic reaction. In this reaction, heat is released. All right. So these are the profiles that you have got to keep in mind in terms of endothermic, exothermic. What is enthalpy? You have got to keep in mind what is enthalpy of formation and what is enthalpy of decomposition. Whenever as I explained you earlier, whenever del H0 is given, that is bond enthalpy, that is breaking of bond. Whenever del FH0 0 standard enthalpy of formation is given. This is for formation of enthalpy. Value magnitude wise both are same, but there would be difference only in sign. One would be positive, other would be negative, as we saw. All right. And so we have got to keep in mind what are those formulas which are to be used. Got to be very clear about the formula that we are to use. All right. So hope this helps. Now let's get into further application of thermochemistry.